I'm going to prove the formula that the area of a triangle equals one of its sides times one of its other sides times the sine of the angle between these two sides A and B divided by 2. And we have three cases. First case is when gamma is less than 90 degrees, such as here. Second case is when gamma equals 90 degrees, such as here. And third case is when gamma is larger than 90 degrees, which is the case here. Now for this case, I'm going to drop the altitude like this, and then in this right-angled triangle, we have that the hypotenuse is b and one of its acute angles is gamma. And therefore, this side is b times the sine of gamma. And hence, the area of this triangle is its base a times the height b sine of gamma divided by 2. And so the area is a times b sine gamma divided by 2. For the case here, we know that the area of a right-angled triangle is a times b divided by 2. Because a times b is the area of this rectangle here, which is twice the area of the triangle. But now we need to know what sine of 90 degree is, and we forgot, unfortunately. For this, we're going to reference the unit circle, and let's see. The 0 degree angle is here, the 90 degree angle is here. So we need to see what sine is associated with this point. We know that the sine is a vertical projection, and so taking this point, its sine would come here, so it would be 0. Then the sine increases until we get to this point, at which point the sine is 1, and then the sine decreases again here until we get to 0. So calculating the sine essentially comes down to playing with the points on the circle by projecting them onto this vertical line and seeing what distance they make with the point here, the origin. For 90 degrees angle, we have that this point makes a distance of 1 with the origin, and therefore sine of 90 is 1. And therefore, the area of this triangle can be written as a times b times the sine of 90 divided by 2. And now for the third case, we need to draw the altitude from this point to this line here, so it comes externally right here. And the area of the triangle would be the base a times the height, the length of this segment, divided by 2. We know that this angle is gamma, and therefore this angle here, the complementary one, would be 180 minus gamma. Then in this triangle, it's a right-angled triangle with hypotenuse b, and one of its angles is 180 minus gamma. Therefore, this side is b times the sine of 180 minus gamma. And so the area of the triangle would be a times b times sine of 180 minus gamma divided by 2, which is written here. And we need to prove that in all cases, it's equal to a times b times sine of gamma divided by 2. So what is left to prove is that sine gamma equals sine of 180 minus gamma. Now remember how we proved it. Suppose that in this unit circle here, this angle corresponds to gamma, then 180 minus gamma would be this angle here, and the two red lines would be symmetric with respect to the y-axis. Therefore, their projections onto the y-axis would correspond to the same number right here, this distance, which is sine of gamma and sine of 180 minus gamma, and so the two are equal. Hence, in all the three cases, this formula here applies. Now I'm going to show you a method for proving that 3 points lie on a straight line. First, let's consider the case in which we know that they lie on a straight line. So essentially, we have a triangle, and a point is chosen on one of its sides, and then we connect it like this. Suppose that we know all the red parts in the picture. So we know the length of x, we know the length of y, we know the length of z, and we know the values of the angles alpha and beta. Then there is a relationship between these 5 quantities. Obviously, the area of this triangle plus the area of this triangle equals the area of the large triangle. And so x times y times sine of alpha divided by 2, which is the area of this triangle, plus y times z times sine of beta divided by 2, which is the area of this triangle, equals x times z times sine of alpha plus beta divided by 2, which is the area of the large triangle. Now taking this equation, multiplying it by 2 to cancel out all the 2's in the denominator, and dividing it by x, y, z, we get sine of alpha divided by z plus sine of beta divided by x equals sine of alpha plus beta divided by y. And this here is the relationship between x, y, z, sine of alpha, sine of beta, and sine of alpha plus beta, which would tell us whether these 3 points lie on the straight line. Indeed, suppose that we don't know if this point, and this point lie on the straight line, so they might as well be vertices of a triangle like this. And consider the area of this quadrilateral. It could be expressed as the area of this triangle, which is x times y times sine of alpha divided by 2, plus the area of this triangle, which is y times z times sine of beta divided by 2. Or it could be expressed as the area of this triangle, which is x times z times the sine of alpha plus beta divided by 2, plus the area of this triangle here, which we need to prove is 0. right? Suppose that the area of this triangle is 0, then the only way this could happen is if that this point lies on this line. So S, the area of the quadrilateral, is this expression, and also this expression, where S0 is the area of this triangle, which we need to prove is 0. But if we know that this is true, and we know that this is true, therefore, we know that this part will cancel out with this part, leaving 0 on this side and S0 on that side, which means that S0 is 0, or that this point lies on this line, which we had to prove. This is the optional problem. We have a right-angled triangle with right angle here. This is its incircle, and this point here is its incenter. The two tangency points here and here are connected, and then from this tangency point, we draw a perpendicular line to this line here at this point, and so we need to prove that this point, the incenter, and this intersection point lie on a straight line. And here's the solution. The incenter is the intersection point of the angle bisectors in the triangle. Therefore, this line here is an angle bisector, so if this angle is beta, then this angle is beta. And we know that this is the tangency point to the circle, and this is its center, and so this angle is 90 degrees. Since this is an angle bisector of this angle, then this equals 45. Then in this right angle triangle, we have that this is 90 and this is 45. Therefore, this angle here is 45. And so this triangle is isosceles. So if this is r, then this is r. But we know that this is a tangent line to the circle and this is a tangent line to the circle. And therefore, this equals r. And so this is r, and this is r also. In general, this here is a square with side length r. We know that this is an isosceles triangle because these are tangent lines to the circle, and this angle is 2 times beta, therefore this angle equals 90 minus beta. Now from the alternate segments theorem for this triangle, we know that this angle corresponds to this arc, and so it equals this angle. And from the sum of the angles in this triangle, we know that this angle here is beta. From this isosceles triangle with angle 90 degrees, we know that this angle equals 45, and therefore this small angle here is such that 45 plus beta plus that small angle equals 90 degrees, which is this angle. And so this small angle must be 45 minus beta. Let's zoom in a little bit. So we got that this angle here is 45 minus beta, that this length is r, this length is r, and this length is r. Now since in this right angled triangle we have that this is r and this is 45 degrees, then this hypotenuse must be r divided by sine of 45 degrees. And finally, from this triangle, we know that this is r divided by sine of 45, and therefore this side is r times cosine of beta divided by sine of 45, because this angle is beta, and the cosine of beta is the ratio between the adjacent side and the hypotenuse. Also, in this right angled triangle, this angle is beta and this is r, and therefore this side is r times cosine of beta divided by sine of beta. And hence, we have the length of this segment, the length of this segment, and the length of this segment, and we have the angles here and here between these three segments. And therefore, we can show whether this point, and this point lie on a straight line by using the equation we've learned. So we have to prove that sine of 90 degrees divided by r cosine of beta over sine of 45 plus sine of 45 minus beta divided by r cosine beta over sine beta equals sine of 135 minus beta, which is the sum of the two angles, divided by r. We can simplify this expression by substituting sine of 90 degrees with 1, by cancelling out the r here, here, and here, and by noting that sine of 135 minus beta equals sine of 45 plus beta, because sine 45 plus beta and 135 minus beta have a sum of 180. And we know that if two angles have a sum of 180 degrees, their sines are equal. Sine of gamma, for example, equals sine of 180 minus gamma because their sum is 180. So we get this expression here. We can simplify it even further like this. Now note that sine of 45 plus beta equals cosine of 45 minus beta, because the sum of 45 plus beta and 45 minus beta is 90 degrees. And we know that the sine of an angle, for example sine of gamma, equals the cosine of 90 minus gamma, because the sum of gamma and 90 minus gamma is 90 degrees. So I rewrote sine of 45 plus beta as cosine of 45 minus beta, and I put this expression on the other side with a minus sign. And now the task is to prove this equality. To prove this statement, I'm going to use this picture here. Let me explain. We have a triangle here with angles beta and 45 degrees. This is the altitude in the triangle. This angle here is 45 minus beta because the sum of the angles in this triangle must be 180 degrees. Now, because of the sum of the angles in this triangle, this angle must be 45 plus beta. This point here is the circumcenter of this triangle, so the center of its circumcircle. This means that this point is the common intersection point of the three perpendicular bisectors of the three sides of the triangle. So this perpendicular bisector of this side, this perpendicular bisector of this side, and this perpendicular bisector of this side all intersect in this point, for which this equals this equals this equals r, the circumradius of this triangle. From the properties of the circumcircle and its center, we know that if this angle here is beta, then this angle here, with respect to the center of the circle, is twice as much, so 2 times beta. Since this is an isosceles triangle, we know that this angle equals beta. This is an angle bisector, an altitude, and a median at the same time. Similarly, since this angle is 45, this one is twice as much, and then this, if this is the angle bisector 45, 45, then this is also an altitude and a median. But this triangle is a right angled triangle because this is twice the 45, which is 90 degrees. And therefore, the median to the hypotenuse equals half the hypotenuse. And so this equals this equals this. It means that this triangle is isosceles. So this angle is 45 and this angle here is 45. Therefore, this angle must be 45 minus beta. And in this isosceles triangle, this is the angle bisector, altitude, and median to the side. Now I'm going to take this picture and rescale it such that this distance, which right now has a length of r, transforms to a segment with length 1. Or in other words, we multiply all the distances by a factor of 1 over r. Since scaling preserves shapes, the shape of this construction is exactly the same. It's just that all the distances on the picture got r times smaller. Now, from this triangle, which is a right-angled triangle with hypotenuse 1 and an angle 45 degrees here and here, we know that this length is sine of 45 degrees. Similarly, this length is also sine of 45, and so the length of the whole segment here is 2 times sine of 45 degrees. From this right-angled triangle, we know that the hypotenuse is 1, and this angle is 45 minus beta, and so the length of this would be 1 times cosine of 45 minus beta. And similarly, the length of this is also cosine of 45 minus beta. So the length of the whole segment is 2 times cosine of 45 minus beta. From this right-angled triangle, we know that this is 1 and this is beta, so this is sine of beta, and therefore this whole segment is 2 times sine of beta. From this triangle here, we know that this is 2 times sine of beta, and this is 45 minus beta. Therefore, this is 2 times sine of beta times sine of 45 minus beta. Finally, take a look at this right-angled triangle here. The hypotenuse is 2 times cosine of 45 minus beta, and this angle here is beta. Therefore, this side here would be 2 times cosine of 45 minus beta times the cosine of beta. Now obviously the length of this segment plus the length of this segment equals the length of the whole segment. And therefore 2 times sine of beta, sine of 45 minus beta, plus 2 times sine of 45 equals 2 times cosine of 45 minus beta, cosine of beta. Hence we get the following equality. We can cancel out the 2's, we can bring this term to the other side, and here we have it. This is the exact same equation which we needed to prove here. And so, problem solved. Here, you might rightfully ask, well, how do we think of such a construction? This was completely out of the blue. And you would be right. In fact, trigonometry is a tool that allows us to prove equations like this automatically. We still haven't developed the tool yet, so that's why we need to get such a construction. But in the future, you're going to see how such equations are going to seem obvious to you, and we won't need to draw anything else to prove it.